numerical differentiation is defined by dy by dx, differentiating one with respect to the other. If I want to do the forward interpolation, that means the present value with the next value, then I will go for the Newton's forward interpolation. Then I will use this symbol delta F0. This Newton-Cotes method is for uniformly spaced interval of values. In this today's session, you are going to learn about the numerical integration. In today's session, I am going to talk about the numerical integration. If you observe this, this is the lower bound and this is the upper bound. We have an integrand here. We have a dx with which variable I am going to integrate. That is, dx is the variable that is going to change with respect to x. dy here, y is equal to f of x. So f of x means y. So y is going to change with respect to x. This can also be written as dy by dx. So if that is the case, the reverse of differentiation is integration. So I am considering the integration of this f of x dx. So there are two different strategies to develop the numerical integration. That is, one is similar to what we have adopted to numerical differentiation. That is, numerical differentiation is defined by dy by dx, differentiating one with respect to the other. That is, we approximate the polynomial for the given function and integrate that polynomial with the limits of the integration. What is the limit I am considering here? A and b are the limits I am considering here. So if that is the case, this restricts us to integrate the function known at discrete tabular points. If these points are uniformly spaced, then the corresponding integration formula is called as Newton-Cotes formula for numerical integration. Suppose if a is equal to 3, b is equal to 10, then what is the space between these two terms at every interval? If the step size h is equal to 1, then 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. So we have these terms here ranging from 3 to 10. What is the interval space between these two? It is 1, it is 1, it is 1, 1, 1, 1, 1. If it is uniformly spaced, then the corresponding integration formula is called as Newton-Cotes formula for numerical integration. On the other hand, we know that the function explicitly but could not integrate in the usual means because of the nature of the function. Then we can use the concept called quadrature rule to find out the approximate value to the integration. So please note that we are using the quadrature rule for the values which is not uniformly spaced in the interval. For example, 3 to 4, 4 to 6, 6 to 8, 8 to 9 and 10. So this is called as a non-uniformly spaced intervals. In these cases, we have to employ the quadrature rule method. This Newton-Cotes method is for uniformly spaced interval of values. So if that is the case, let us consider the Newton-Cotes formulae. If the function values are known at uniformly spaced points, then as we have already discussed in the chapter interpolation, we can find the polynomial degree n with the n plus 1 data points, which approximates the function at non-tabular points and passes through the tabular points. What does this mean? That means if the values of the interval are equally spaced, then the Newton-Cotes method performs the task of finding the polynomial which approximates the function of n plus 1 data points. So to avoid these large errors during the time of numerical integration, that is divided into subintervals, and the polynomial of the lower degree is obtained in these subintervals, Yes. That means 3 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. Here we are finding the uniformity in the interval except this. So we have a difference of 2. So we will divide this into sub-problem, that is 1, 1. So that the interval will be 4 and 5. So in between these we have 1 and 1. So this is how we are going to do the sub-intervals information. So if that is the case, by adding these values obtained in each of these sub-intervals, the following discussions, let us consider 3 widely used Newton-Cotes formula. That is this. By adding the new value, that is 4 to it, I'll get the equally spaced intervals between the two values. The same thing is explained there. If that is the case, we have to approximate the function f of x dx from x0 to x1. What is this x0 indicates? X0 indicates the lower bound. X1 indicates the upper bound. So if that is the case, P1 of x dx is going to be integrated between the limits x0 and x1. If that is the case, f of x0 plus r into delta f of x0 indicates that there is a difference in f0 and f1. That is called as Newton's forward difference formula. The same thing is going to be compared with this Newton-Cotes formula. So if that is the case, we have the dx here. Please see to it here. R equal to x minus x0. That means the difference of this is determined with x1 minus x0 is equal to h. That means it is delta f0 equal to f1 minus f0. That is the difference of f1 and f0 is assigned to delta f0. That means the delta. What about the gradient? Backward interpolation. Suppose if there is any value which needs to be interpolated with the previous result, then we use this symbol. If I want to do the forward interpolation, that means the present value with the next value, then I will go for the Newton's forward interpolation. Then I will use this symbol delta f0. So f1 minus f0 is obviously equal to delta f0. The same thing is expressed as x1 minus x0 is equal to h, which is a step size here. So observe this here. H of f0 plus r into delta f0 dr. I am using the word r here. So x changes to r. It becomes dx from dx to dr. So we have. So if that is the case, if I further simplify this term, I'll get h into f0 plus 1 by 2 delta f0. So this further simplified into h by 2 into f0 plus f1. So this is how we are going to calculate that. If that is the case, we have error in the interval between x0 and x1 is going to be calculated as this. R into r minus 1 divided by 2 factorial, because we have two values here. So h square f double dash of 1 dx is calculated. Then we have third degree polynomial here, h cube of f dash f double dash of this value. So we have 1 by 2 factorial is what? 2 into 1, that is 2. But for 3 factorial we have, what is the value? 3 into 2 into 1. But we have one more value here, it divided by 1 by 2 is there. So this becomes 6 into 2, this becomes 12. So for the third degree polynomial. So this is how we are going to calculate that. The same thing is explained here, the total error here. Now, geometrical interpretation is going to be done now. When the value of a is equal to x0, xn is what? B. B is equal to xn. So, the curve f0 to fn is indicated by this term. Suppose if there is an area which is of this, it is very easy to calculate this area in the form of a rectangle. That is, length into breadth is going to be obtained. But there is an area which needs to be computed like this. There is an area which is going to loss here. So how can we find out this area which is a loss? How can we find the area which is a added, which is an added here? So all these informations are calculated with the help of an integration. Not just integration, numerical integration. This numerical integration helps me to calculate this total area. from here to here, here to here, here to here, and then here to here. So we have an interval like this. So I'm going to apply the trapezoidal rule. What does the trapezoidal rule indicate? This is the rule. That is h by 2 into fi minus 1 plus fi. This gives me the formula of to find out the trapezoidal area. So if I consider that f of x dx here, between the interval x0 to xn, I have this term. Suppose if there are n number of terms, x0, x1, x2, x3, x4, so on up to xten, where n is equal to 10, n is equal to 0. So we have these terms here. For the formulas like this, h by 2 into, this is called as this trapezoidal rule. This trapezoidal rule indicates that f of x dx, that means p2 of x dx, ranging from x0 to x2. Then we have r into f delta f0, r into r minus 1 divided by 2 factorial, that becomes 2 into 1, that is 2. But we have to multiply it by h by 2, so this becomes 4. For the third degree, we have r into r minus 1 into r minus 2 into delta cube f0 dx divided by this, divided by 3 factorial. What is the 3 factorial? 3 into 2 into 1. This becomes 6. This has to be multiplied by h by 2. So 6 into 2, this becomes 12. The same thing was explained in the earlier slides. So see here, we have the terms like this. Then we have delta h into, we have the terms here. H is taken common factor. Then h into f0 plus 4 times f1 plus 3 times f2. Since we have delta f0 equal to f1 minus f0, delta square f0 equal to f2 minus 2 times f1 minus f0. That is the formula we are going to use here. So the integration of this is defined as f of x dx, which is ranging from x equal to n minus 2 to n. So this is how we are going to find out this. So we have this term h3 here. So h3 here. So this formula is also called as Simpson's formula. We have two different types of Simpson's formula, that is Simpson's 1/3 rule and Simpson's 3/8 rule. The problems are not yet taken, so don't worry. The problems are asked in the question papers of final years, of final semester, of this type, that is Simpson's 1/3 rule, using Simpson's 3/8 rule, using trapezoidal rule. We have few more types of methods like Runge-Kutta second order method, Runge-Kutta fourth order method. All these has to be solved. This is how we are going to calculate the trapezoidal rule method. Along with that, we have the Simpson's 1/3 rule method and Simpson's 3/8 rule method. So this is the theory of this. But the problems are not yet taken, which will be explained in the next and subsequent sessions. The problems are very, very important from the point of view of examination. Please concentrate on problems. This is a theory. Thank you very much. Thank you one and all.